All right, so I think we can start. Okay, so now we have our first invited talk, which is given by Fabio Zanasi from UCL and University of Bologna. And Fabio will talk us about category theory machine learning. So Fabio, please go, the stage is yours.
Thank you. Okay. Yeah, I was saying it's nice to be in front, especially of this audience. I'm used to try to sell category theory to computer scientists or machine learning people, software engineers, but already sold. So that's a different perspective. And in fact, I've been this morning to the talks you gave, and I am afraid my category theory is more like kindergarten category theory to some of you. So it's very simple one, but let's say it's an applied perspective. So it's kind of a means to an end. And that work is indeed about how to apply some methodologies, some perspectives, some techniques from category theory to the analysis of machine learning and what that can bring to our understanding of this field and how can also be useful for people working in that field. This research line, which I've been now working on for the last couple of years, draw inspiration from analogous approaches that me and other people in my community, which broadly speaking, you can think of as the community that you see, for instance, at ACT, at Applied Category Theory. So this it draws inspiration from this series of approaches trying to give a categorical semantics to various kind of component-based systems that arise in different fields of science, and to do so in a kind of a uniform manner. So you will notice many of the systems that are enumerated here, they are expressed as some kind of graphical formalism. And the idea is precisely that traditionally these systems are described in terms of combinatorial techniques, combinatorial methods as graphs, whereas using category theory, we can actually take these graphs and make them into a formal syntax, some kind of algebraic object that we can reason about in a much more powerful way. How that works in a nutshell, let's see just on one of the examples I gave in the previous slide. This, for instance, is a signal flow graph. This is a kind of circuit you find in control theory and engineering to, for instance, model linear dynamical systems. You can think of signal flowing in and passing through some gates that transform it in some way. Now, the idea of this kind of approaches is that this object, which so far is just a graph, becomes actually a formal syntax, which you can express just using a grammar, as you would do with a programming language. And this syntax generates an object, a graphical object, which is the one here on the right, to which we can map our original graph. So if since you're used to this kind of reasoning, I can immediately say, when you see here this kind of grammar, what I'm doing is simply to generate a symmetric monoidal category by generators and relations. So these are the, let's say the generating morphisms of the category, and these are the so-called, you may call them structural morphisms. So we have the identity, the symmetries, the empty, and we compose them sequentially and in parallel. Of course, yeah, there are typing concerns that I'm kind of abstracting away, but hopefully you get the idea. So why we do this? Because in here, what we can say about this object is pretty much what we can say in terms of combinatorial reasoning, what we can do about graphs like reachability and the like. What we have on the right here is instead a term of this syntax. So it's actually a string diagram. So it's a morphism in the category generated by this syntax. But now, of course, we can treat it as an algebraic object, study equational properties. Also, from a more practical viewpoint, we can reason about it compositionally. So in this one on the left, if we try to cut it in half, it's a bit unclear how each half, what is the meaning of each half. This is not even a well-formed signal flow graph in the traditional theory. When we go on the right, instead, making such a cut makes perfect sense. We are simply considering a string diagram as the composite of two smaller diagrams, and there is a very simple and elegant way to assign meaning to each of these objects separately as a linear relation, for instance, so a subspace over the reals, and their composite will give us the behavior of the whole system. So this is the compositional reasoning that this kind of analysis enables. Obviously, this is at the very basic level. Then there are many developments you can make on the top of this. So imagine now trying to export this kind of approach, which is essentially the approach of programming language semantics, no? But now generalized to component-based systems. Imagine to try exporting it to the setting of machine learning. Just as in the case studies we've just seen, in machine learning, we have many different kinds of graphical formalisms where there are interconnected components. We have to be aware about resources being used, and we have very complicated schemas that we wish to study in a more principled and simple way. Here, what I'm just doing is to throwing at you some kind of different kind of architectures for neural networks, for instance. We have a convolutional neural networks with convolutional layers. We have some reinforcement learning. We have some deep learning, and so on. So what is that we want to say about this system using the techniques we just described? So first of all, as usual, there is a desire for uniformity. Here we have many different algorithms, many different models. Their theory, I wouldn't say is developed somehow independently, but to some extent, of course, as you know, when there is an engineering problem, there is a tendency to develop a solution or a way of thinking that is specific to that problem. Now, obviously, what we want to try to do here is to recast these techniques and new ones into a more systematic, uniform setting where we can think about all these different models in a uniform manner. This leads, in turn, to a desire for better programming principles. Now, obviously, there are many suites that have been developed software for reasoning about machine learning. Think about TensorFlow, PyTorch, and so on. Each one takes their own primitives, no? For what kind of mathematical structures we should use when we reason about machine learning, when we design new algorithms, or when we want to specify their properties. And who says those are the right structures? This is a bit the same thing as in concurrency theory, no? Where it's still kind of unclear what are the right structures we should pick as fundamental. Now, I think category theory gives us good information, good evidence on what kind of structures could be suitable. So this is a kind of research that we want to contribute on. What kind of design principles, what kind of primitives could be good or on which to develop a nice programming environment for machine learning. There are two other issues which are also concerned with how machine learning interfaces with the general public, with society at large. The first one is to do with something called explainability. Here, essentially, the idea is that people use machine learning algorithms in a form or another every day, but usually their interface is very limited. They are given an answer, but they don't know how that answer was computed on the basis of what evidence, what was the line of reasoning that led to it. Think about going to the bank and you want to get a mortgage, a very important decision in your life. And on the other side, you get an accountant that runs your data in a program, and then the program says, no, this person cannot have a mortgage. And they say, why? And they say, well, the computer said so. No, that's the kind of thing that we want to explain. So that's there is a societal concern over there, no, for not only being able to use these systems, but to understand why they reach certain conclusions. Now, my stance, I think our stance as people working in semantics should be that really the semantics is able to inform this kind of reasoning, like is able to inform how these algorithms actually work, what is their mathematical meaning. This also leads to another related but separate issue, which is the one of trustworthiness. We all know very well from for program verification, there are areas of software development in which there is the need for critical systems to be safe, to be trustworthy. There are systems that they shouldn't fail, so we should have kind of some correctness check, some way of proving them to be correct or to specify some other kind of property. And obviously the same applies to machine learning. So there is there is a theory of formal verification that tries to apply to machine learning the same kind of principles and guarantees that we know very well from the theory of programming languages. But this theory is very early stage, and I think a categorical semantics for machine learning could inform it just as well as the categorical semantic of programming languages was able throughout the years to inform formal verification. So this is a bit, let's say, the context, why we are doing this, why it could be interesting for us, but also for the other people. And now I'm going to present, we are going to narrow it down because obviously it's a huge enterprise to try to capture machine learning in general. Machine learning means many things. So let's try to be a bit more convincing and narrow by focusing on a case study. So gradient-based learning is a kind of machine learning that is very simple yet fundamental. It's essentially how neural networks typically are trained. This is a scheme, a little picture presenting how gradient-based learning works. So imagine you have your model, a neural network. So this is a graph with nodes and arcs between them. And you have to imagine the information flows left to right. There are some weights on these arcs, and that express a certain function that the neural network is computing, a function over vectors of real numbers. Now, an input comes in, for instance, a picture, and your neural network is giving an output, usually called a prediction. For instance, we can imagine this network is trying to figure out whether the input is a cat or a dog or another animal. Initially, at different stages, the prediction could be wrong or could be just partially correct. For instance, in this case, it's saying probably it's a cat, but they're not quite sure. So this information is fed into the loss map. The loss map is simply a function that compares the output of the computation with a set of labels. So the labels here are actually the true answers that the machine was supposed to give. And for instance, in this case, the actual answer was that was 100% a cat, what you see in the picture. So the loss map compares this with the prediction and gives back, let's say, usually the difference, but let's say the error that the prediction contained. This is fed into something called an optimizer, which is simply yet another little algorithm that what it does is to change the parameters, so the weights on the arcs, based on the information of what the error was. And this is where the gradient computation happens, which gives the names to the algorithm. And there is yet another parameter, which are the learning rate. And the learning rate is just a parameter telling us how dramatically we should try at each step to change the parameters towards a better algorithm, an algorithm that computes a better answer. So a couple of points. Here we use the labels. This is called supervised learning, where actually there is a set of real answers that are given. There is also unsupervised learning out there, which we leave out of the picture for the moment. But we can also do it if you're curious. Another thing to see here is that, as you can see, there is information flowing in different directions. So there is the function being computed, sort of left to right, and then there is some information flowing back to the net. And this is why this is suggestively called out by me, but it's like how it's actually called backpropagation algorithm most of the time. So this is the gradient-based learning algorithm, very shortly. As you can see, it has lots of moving parts. It has lots of things that do little things. And as theorists, our first impression is, how can I clean this up? How can I try to make this more uniform, more systematic, what principled. What is the semantics of this? No? What kind of mathematical gadgets should be able to model each of these components, and how can I describe their interaction? So said in more elementary terms, what are the fundamental structures that underpin this process of gradient-based learning? So the answer that we came up with in our own approach, then obviously there are many different approaches, is that we are trying now to turn this diagram into this diagram. So at first, it seems that we didn't gain much, but actually they're very different. So this one is just a funny picture with no formal meaning. This one is actually a string diagram in a certain category. So this is going to be a morphism in a certain category. These boxes here are also morphisms. These lines, they witness some kind of composition happening in this category. So what we are going to have at the end of the process here is a fully fledged algebraic object which you can handle in the usual ways that we like. And what are these boxes here? Well, they are something that we are going to call parametric lenses. Okay, if you're familiar with lenses, those lenses there. The main gist is also we just not establish that in machine learning can essentially be expressed in terms of lenses, but we represent them as string diagrams that kind of mirror the information flow happening in the original gradient learning algorithm. And the learning as a whole, the algorithm that is expressed here, will just be reduced to lens composition. So here we really try to operate a reduction of all these different aspects and traits that appear in learning to a single primitive concept, which is the concept of a lens and of lens composition. So this is the primitive we kind of claim, and we claim is good for the semantics. We claim is good also as a programming principle and for other things that we will discover along the way. So this is let's say the roadmap. What we are going to do. Is there any questions so far? Things you're curious about? Okay, if there is no standing issue, let's get on from here. So now what I'm going to do is to define the categorical entities that we're going to use to model this gradient-based algorithm. A parametric lens is a parametric morphism with lens structure. So we decompose this statement. First of all, we have a parametric morphism. Take a category C. We represent morphisms as simply string diagrams F from A to B. A parametric map simply is a map that is parametric in a certain parameter space P. So you can build a category pair of C where morphisms from A to B are arrows that goes from P times A to B for a certain parameter space P. When you compose them, you enlarge your parameter space. So of course, you need the Cartesian product in this category. And you can also have another operation, which is called reparameterization, in which you change your parameter space. So essentially, as you see here, you simply plug a new alpha and q on the top of the original parameter space F, and you convert your q's into p's along the way. Already from this slide, you can see how convenient it is to use string diagrams here, because we are going to separate parameters from inputs and outputs, and later on we are going to add even more interchange of components. And string diagrams really help us keeping separate these components and really see what's going on there in terms of information flow. As for instance here, the parameter space is coming always from top, and inputs and outputs instead occupy the vertical dimension. The horizontal dimension of the diagram. As a first example of why we want parameters around, a neural network is as an example of a parametric map. Take the category of smooth functions over vectors of the reals. So in this case, a neural network is simply a morphism in this category. You have your weights, they constitute this parameter space P, together with the biases. So the bias is like the nonlinear part of your computation. And instead, the inputs to the outputs mapping is modeled by a morphism that goes from R to N to R to M, where N is the dimension of the inputs, and M is the dimension of the outputs. Of course, this can be made more fine-grained, if you like. Neural networks are known to have layers, and obviously we can account for these layers. As for instance, this network could be the composite of two different parametric maps, one for each layer, and you can make this even more fine-grained if you like. Yes?
What does it mean?
Differentiable, so differentiable functions. Okay. So the second ingredient that we throw in is the lens structure. So the lens structure is going to account for this ability that neural networks have to feed backwards information in order to change their own definition. A lens, in a nutshell, is a morphism with a reverse mode. If you want to express this idea in categorical terms, you will say that a lens on a category C goes from a pair of objects A prime to BB prime in such a category, and will be a gadget with two morphisms. One is a get map from A to B, so it refers only to the first components in these two pairs. And the second is a put map that goes from A times B prime to A prime. So lenses are older than category theory. They first appear in database theory, but there is an interesting historical survey by, I think, Jules Hedges, and also studies by Valerio De Paiva, tracing this back to the dialectical interpretation. I see you, Fosco, being puzzled. You don't agree with this? No. Ah, okay. Anyways, I was saying lenses are much older than this. They trace back, as I was saying, to the dialectical interpretation, and they have some other ancestors in the history of mathematics and computer science. They've been rediscovered many times. A notable one, not so much time ago, and in computer science, is database theory, where this terminology comes from. So the get map is essentially a map that gets you to access a certain record and extract a value B. And the put map allows you to update a record. So you have your location A, you get a new value, B prime, and you get a new location A prime, okay, defined out of this. And this is also why we use A prime and B prime. In a generic lens, A prime and B prime do not need to have any relationship with A and B. However, in many cases, and also in the case we will study, they do have a relationship. And we use the prime here to pinpoint that this will be a change in A and this will be a change in B. So if you think about a lens as a string diagram, it simply may be something like this, okay, where I say that I have an A prime and a B prime. However, this is not very enlightening because it doesn't say anything about the get and the put map, and it doesn't allow us to really describe the information flow, the forward and the backward mode that are instead what the lens is trying to describe, to suggest with its structure. So this is why we use a different string diagrams, class of string diagrams, which are these ones, in which you see the A splits into two. It goes in the get map to get a B, and it goes backwards in the put map together with a B prime to get back an A prime. So this is suggesting that the get map is the forward mode, and the put map is kind of a backward mode. It is suggesting that A are some kind of the inputs, and B are some kind of the outputs. And now you're wondering, what am I doing here? Because I've said all the time, string diagrams are formal entities, they're morphisms in a category. What are we drawing here? In which category do these things live, and how we are even allowed to draw them that way? Well, the answer comes from, let's say, a little detour we can make from the theory of the category lens of C. It turns out that if you take presheaves over lenses, you end up in a category of so-called Tambara modules. This is a category of profunctors. There is a paper by Guillaume Boisseau, which some of you may know, in which he describes essentially this category of Tambara models and how you can express lenses in it. So we all know that any category has a faithful embedded in its own presheaf category, and this is what we are exploiting here. So anytime we have a lens, we can see it through the embedding in its own presheaf category as a Tambara module, and we can access the very nice string-diagrammatic language of the bigger category in order to describe it. Now, I'm not going into the details of, let's say, how this category of string diagram is actually defined. You can find this in the paper. I can also give you the reference afterwards. But anyways, this is what we are using here. We are when we use this notation of string diagrams to describe lenses, we are not cheating. We are just using this embedding. So we are still completely formal, but we are able to use a much nicer notion. Yes?
But the product is an arbitrary monoidal product, or that to be Cartesian?
So in lenses, it's Cartesian. However, in this theory here, there is also the study of an arbitrary monoidal product. And lenses, when your monoidal product is not necessarily Cartesian, are called optics. This is the level of generality of the paper I was mentioning. So you can develop that theory. And in our case, the approach I'm describing, we assume the Cartesian product, but I don't think it's really tied to that. I think you could make an effort and generalize it if you want. Okay, so having seen what lenses are in general, let's see our motivating example, how it turns out in this context. So a neural network is a lens in the same category we saw before. How it is defined? Well, this f here is simply the function that the neural network is computing. And what is the update map? That's the most interesting part. That's the so-called reverse derivative of f. So if you, the reverse derivative is really the part that is allowing me to compute these parameters. And this reverse derivative of f, the type is the following. It takes inputs in A, it takes a change in the outputs, and it gives me a change in the input. So now you see why I use this prime notation. How is this change in the input computed? Well, it's going to be a linear approximation of what it takes to my original x in order for f of that x to be the original f of x changed by the b prime. Okay, so it's the typical thing you do when you take the reverse derivative of a function. In more formal terms, this J here is the Jacobian matrix that takes the partial derivatives of this f with respect to x multiplied by this y. And also this part that we use in our own approach draws from a nice piece of theory, which is this theory of reverse derivative categories, which is an attempt to axiomatize this notion of a reverse derivative in a categorical setting. And this author studied this operation with this type. And here we simply limit ourselves to observe that if you take a function at this reverse derivative, as defined, for instance, in this paper, they form a lens, which is what interests us here. So now is the time to put this together. We have a category lens of C, and we know how to do para. We do para lens of C. And this will be the category where we study parametric lenses. So a morphism is going to be a parametric lens. So it's something that we depict as a string diagram in this way, where the parameters are above. And you see now that this being a lens, there is always a forward and a backward information flow, but for the inputs, the outputs, and the parameter space. Composition is along the middle part. And we can also do reparametrization, just as we did before. So this is how it looks like, a neural network, if we use the formalism for lenses that we described before. And you can already start seeing how things are gonna get more concrete, because the description we made so far is very high level. It's still hard to grasp at what level we get to see those phenomena that we saw at the beginning where we explained gradient-based learning. This is where we start to see them. So if you unpack the lens that we saw before, you see that in the computation of f, the function that the neural network is computing, it contributes the parameter space P and my original A, this giving me a B. At the same time, I have another device in my network, which is this reverse derivative, which is taking the P and the A, but is also taking a change B prime, and is giving me back some change in the parameter space and in A. So you know that the gradient descent learning is all about changing your parameter space. So here already you can start seeing that types are going to match in the sense that we are going to change the parameter space P using this P prime out of R of F. What about A prime? How do we care about the change in A? Well, for now we don't, but we will come back to that point. Nothing will be wasted here. We also use this at the very end. I also want to say this is like the, say, layer level view, but just as we did before for the neural network as a parametric map, we can make this more fine-grained. So this is, for instance, how a single layer of a neural network will look like as a composition of parametric lenses. We can imagine of having a parametric lens for the linear part, one for the bias, so the nonlinear part, and one for the activation layer. And then we compose all of this together. So it's not just that parametric lenses are able to describe a neural network as a single organism, but you can actually narrow that down and have a more detailed description. So what we have so far of this picture is essentially this. We have described this component here, the model, okay, which is AA prime, BB prime, and PP prime. Now I want to move to the other components, because of course what we have now is barely half a description of the algorithm. No? We just have our F, our reverse derivatives. There is nothing really telling us how what optimizer, for instance, we use to change the parameters, how the learning rate, the loss map, how they all enter the picture. So we need to model those components as well. And it turns out they are all modeled exactly the same. I would say that's perhaps the thing that surprised us the most. You may think that these different things require different kind of modelizations, but it turns out they are all nothing but different lenses of different types, and their interaction is completely described in terms of some kind of lens operation, which could be composition or reparametrization. So now we move to see the optimizer, which I think is the less trivial part among those that are left. The optimizer is an algorithm that usually tells you, given the error, how do you use it to update your parameters. So this is how you do, for instance, in basic gradient descent. In basic gradient descent, we are going simply to make a sum of the original parameter with the change in the parameters that we want to make. And this is how it looks like in our framework. So it's going to be a lens of type PP to PP prime, where P is our parameter space. So we take this lens and we turn it 90 degrees, and we use it as a reparametrization operation on the top of our model. So remember, our model is spitting out these P primes as a computation resulting from the reverse derivative. These are here using the computation. They are summed using the put map, and they are fed back in here. So this optimizer is really doing the job of updating our parameters the way we like. Now, this wouldn't be very enlightening if we just could do the simple case, but it turns out we can do just as well all kind of more complicated optimizers that people use. People don't just use basic gradient descent. They use other algorithms called, for instance, AdaGrad, Adam, Nesterov momentum. Some of them use also states, for instance. They are stateful computations. They are not just computed point by point. It turns out they can all formalize uniformly as different kind of reparameterizations. So for instance, this is Nesterov momentum, just to show you one. As you can see, the parameter space is a bit more complicated because I'm also including the states, some states in the computation. I have some extra parameter gamma that is not important here, but is all part of the Nesterov momentum algorithm I usually specify. And you also notice that the put map is also a bit more complicated than before. So this is the lens that is going to model these other kind of optimizer. And for all these others as well, we have alternative description, and they all fit the same format, essentially. So we have seen models, we have seen optimizers. I will spend now some words on the loss function and the learning rate, which, and no surprise now, they also turn out to be lenses. This is, for instance, the square error loss map, also described as a string diagram. Something you'll notice here is how the parameters turns out to be the labels that give us the actual answer in the supervised learning. So this is the B. This device here, this string diagram, is going to compare these B's with the answers that the algorithm is giving us, this B here. I also give out some B prime, which I don't use. And this is going here, doing nothing. And here, however, there is a non-trivial part of this. This is also a lens of a very simple kind. And this eta here is going to be the learning rate. So the learning rate is also yet another lens of a very trivial kind. As you can see, it has no outputs and no parameters, just some inputs. And this is going to amplify the rate. So this is actually acting as a multiplication of real numbers. So if you simplify this picture, because obviously we are in a category, we can use equational reasoning. So if we simplify these string diagrams, we get these string diagrams which describes what's going on there. So we have the supervised learning giving us some B. We compare it with the actual answer coming from the neural network. We subtract the error, we amplify it by eta, and this is going to be the change B prime. And this is going to inform our P prime, which is going into the optimizer and going back. So you see, all turns out to be the same as the intuitive picture we did before, but now it's formal, and now we actually understand it. So the first reason why I did all this is because I didn't understand machine learning. So I wanted to understand it on my own terms, and I think this gives a more clear picture of what's going on in there. Yes?
I would expect some link with. I would expect some link between the optimizer and the loss block.
Yeah.
Okay.
Yeah, that's a good point, because that's how it works in the standard theory. In the standard theory, the block with the error and the learning rate is tied up in the is presented usually together with the optimizer. But this is something that we discover by doing this, namely that they still interact, but their interaction is mediated by the model. So the interaction still happens, but you can study them as separated formal entities. So I don't know, I would call this more a feature than a bug, let's say.
So it is something that it is in the block model that is not detailed in this picture.
Yes, but it is detailed. If you take the picture with the model I gave before and you put it there, you will see there is a link. That this is also why we use string diagrams. Otherwise, you will never figure out how the link works. So yeah, that's a point. Another point is, for instance, the gradient computation itself, the reverse derivative. You'll notice is not part of the optimizer, as it usually is. The optimizer is defined independently of the way you take changes. For instance, the simple gradient descent was simply a sum, an addition. So the way you do changes is specified in the model. In this case, it's a reverse derivative, but this opens up interesting possibilities. Maybe you want to do changes using something else, the reverse derivatives, and you can here separate concerns. Okay, so we have basically covered all of this. The remaining part I didn't describe is simply a trivial lens that gives us the inputs. You see, we are still not making anything of the change in the inputs, but we'll do something of them in a variation that we'll see of this picture. So last thing I want to say is, how do we put, well, last thing, not completely, but let's say last thing for the main picture I want to say is, how do we put all this together? Because I said the composition describes learning. So how that is actually true? We have described the individual components so far. If you take the whole lens, because obviously a composite of lenses is yet again a lens, this is very simple. It's actually as a parametric lens, so as a morphism in parallels of C, is simply a map from 1 to 1 to 1 to 1, because you see there are no inputs and not outputs. However, if now you take parameters into the picture, you see you have a very rich space of parameters that are fed into, which essentially are your inputs, your parameters, and you also keep track of your labels that you use in the supervised training. So if now you unpack this lens, especially the put map, because the get map here is trivial, okay, it's the identity, but the put map here is very rich, is this thing here, and the put map is what is doing all the work. So what is the put map doing? The put map takes the inputs, the parameters of the network, and the labels, and is giving me a change in each of these. So how is this change computed? First of all, I use the f, the actual function that the neural network is computing on my input and parameters, and I get some b, which are the outputs. Then you see this b is used here together with the labels. So BP is the actual output, and BT are the labels that I should compare. And this is taken together with the alpha here is the amplification of the error. So I amplify the error and I compute the loss, which compares BP to BT. I take the reverse derivative of this, and this gives me a change in BT and a change in BP. And finally, I take the reverse derivative of f with my parameters, A, and the change in the outputs. And this gives me the desired change in the parameters as the first element. So this is a bit maybe hard to follow, but I just wanted to pattern match the types of these morphisms to show you really how the actual algorithm that is typically used to gradient descent arises from this put map completely. Of course, learning doesn't resolve in a single iteration of this algorithm. Usually you do an iteration of it. You iterate it many times. And this is how you can do it. For instance, you can think of your A and B as your data set. This becomes, in this view, they become the parameters of your algorithm. And the P's that here are parameters, they become input and outputs. So you have your put map, and you keep applying it to your P's, taking the A and B, the data set as parameters, and this will transform the parameters as many times you like, and as a result, you will have the parameters to use in the trained network. So this is how the training would work if we would imagine it as an iterative process, how it happens in actual real life. It's interesting in this picture compared to this that in here, the parameters and the inputs outputs switch roles when it comes to this training process, which in a sense is reasonable, no? Because if you think about machine learning, the real protagonists are the parameters, no? That needs to evolve, and the inputs and the labels are just used as extra ingredients that you use in this learning process. Okay, so let's say we are now done with the generic picture I wanted to present. I want to conclude by showing a couple of variations. So the first variation is something called deep dreaming. Well, let me first say why we want some variations, because the point of doing this abstraction of category theory, of taking all the trouble to recast things in a different setting, is not to just model a specific context, is also to show how it allows us to model different contexts in the same manner or to discover new ones. So the first variation is in the category of modeling other contexts that are known. This is something that people in machine learning literature call deep dreaming. What it amounts to is a trained neural network that takes an input image and changes it according to its bias. So for instance, imagine your network is trained to recognize dogs. So you can think of your network as something taking a picture of jellyfishes and morphing the image until you get some psychedelic dogs over here, okay? This is your over-processed image. This is something that people study. Don't ask me why, but it is a thing. Well, it turns out that we can straight away give a neat description of what's going on in deep dreaming. It just amounts to shifting the optimizer from a box over the model to a reparameterization to another box over the set of inputs. And there is really when we make use of this A prime. So the change in the input is not important in the model, but at the moment we want to reprocess our input image, which is what happens in deep dreaming, for instance, we can think of this reprocessing as the act of giving this change back to an optimizer that is feeding me a new set of inputs. So deep dreaming is nothing but shifting this optimizer box over my inputs and their changes. And you see now my model is assumed to be trained, so I'm not doing anything more with my P primes. Second variation I want to mention is learning in other categories. If you were following, you'll notice what we did is not strictly related to smooth functions or to real numbers. No, we made some assumptions along the way, but these assumptions also hold in other categories. Essentially, we need a Cartesian structure, the structure of a reverse derivative of some kind, of some change. It turns out another category of interest that satisfies this assumption is Boole, which is the category of Boolean functions, which have an operational model in Boolean circuits. So this is a Boolean circuit. In terms of learning, we can see a Boolean circuit as a very simple kind of a neural network, where instead of having real values flowing in and out, I'm just computing with Boolean values, with bits 0 and 1. So we can just take our picture of learning for neural networks, transfer it to the category of parametric lenses in Boole, and try to see what happens. Does it make sense to learn Boolean circuits? You notice that we're using basic gradient descent. Everything else looks the same. The only difference is we are taking a Boolean circuit as a model. The values flowing are now Boolean values. And another interesting aspect is that for the model here, we actually have a description of our F in terms of a circuit syntax that is given to us. Because Boolean circuits have a tradition of being studied in terms of string diagrams. There is a grammar developed in the French tradition, the works of Yves Lafont, Buroni, and other people that study Boolean circuits in this syntactic way. So this we can use to specify our F, and it turns out the reverse derivative can be defined compositionally with respect to that syntax, which I find quite interesting because, as you can imagine, doing it compositionally may lead to some scalability in computing these derivatives, which of course is an expensive process. So this is some highlights of the Boolean model. It turns out it makes actually sense to train with Boolean circuits. We know because we took this and implemented it and tried to learn some data set using Boolean circuits, and the thing was actually learning on this data set. There is some developments there that I will mention in a moment. So I've showed you this picture in general, this lens theoretic approach to this gradient-based algorithm. I've seen two variations as just an example of the kind of variations you can do from the basic picture. What are the benefits? Let's try to come back to what we claim at the beginning as things we like about category theory. So we reach some level of uniformity. All components at work were reduced to a primitive concept, the one of parametric lens, which we identified. We managed to abstract different kind of gadgets, devices, techniques, models, and so on. In terms of this concept, in particular, we covered different optimizer, different models, Boolean and neural networks, also different loss maps, which we didn't cover, but like, for instance, are in the papers if you want to look at. They are all instances of the same picture. Another point is, of course, compositional reasoning. What we did here is to divide the whole of the learning algorithm into simpler components, which we can now chop and rearrange differently. For instance, we may imagine of composing two optimizers. For instance, Nesterov momentum you can think of as a composite of Nesterov and momentum, or we can create new ones by this composition. We can consider the composition of a train together with an untrained model. We can think also of plugging the optimizer in here. There is some direction in meta learning which is called training gradient descent by gradient descent, if any of you is familiar, which means you develop your optimizer using another optimizer. We obviously can do it here. We simply use the optimizer as a lens, as a parametric lens. So there is lots of space there for interesting design choices, which can be done at a very high level compared to the usual engineering practice. Another point I want to make is that because we are using string diagrams, we've been perfectly fine using another kind of syntax or types or logic, which you may like more. But I like string diagrams, and the reason is that you can really see how information is now flowing inside your categorical morphism, where things are going and how they participate and interact with each other. So I think this really is a kind of enlightening way of reasoning about this kind of component-based systems. It has proven itself in other contexts. I think also in machine learning it has merits. So just a few directions going forward. I said I would come back to Boolean circuits. So this is a direction that I am currently interested in. There is a trade-off between learning in a neural network and learning over a Boolean circuit. So the neural network has good performances and is not, it is very accurate, but has worse performances because obviously it's computing over the real numbers. This is to be compared with a Boolean circuit, which has great performances because it's computing the reals, but is less accurate because, of course, the level of precision is not the same as if you're considering a range of real numbers. So there is a trade-off between these two models. There are studies in machine learning of something called binarization, which essentially means to take a trained neural network, binarize it, take a Boolean circuit, and use that. What we can do now is we don't need to binarize. We can train the circuit itself, which is kind of an advancement. And we can even consider intermediate models. So just as the category of Boolean circuits meets the axioms that you need to do this gradient learning, also categories of circuits over polynomial rings meets these same requirements. So we can also think about an intermediate for some middle way through these two parameters. So some family of polynomial circuits that have good performances, but still good accuracy. And this is the kind of field we are currently working on, and especially in something called saturating arithmetic. So this is kind of a middle ground in terms of learning desiderata between neural networks and Boolean circuits. Another point is about programming principles. I said maybe this thing with category theory also give us some interesting idea for libraries, for things to program with when it comes to machine learning. So here are a couple of pointers of tools, prototypes, proof of concepts we developed with these papers we wrote about this. They're not very developed, so don't keep your expectation low, but at least they give some good idea of how they could become something developed. So this is an example using these libraries. These are Python libraries. This is, for instance, modeling a layer of a neural network. So you see this operation here is simply the composite, the categorical composite of these lenses. And this definition of a layer is simply the composite of three lenses. And similarly, when we do the gradient descent, we can imagine we have a method which applies the update to the basic gradient descent in our network and composes it with the loss and the learning rate. So this is just mirroring this picture here that we had, in which we were seeing the learning as the composite of lenses. This is something you can also do as a programming practice, and it's very different from what you do normally. You would not compose functions in order to do learning, but here you can do so. So this thing here suggests a functional style of programming with neural networks, which I think could be interesting and worth investigating further. Last point I want to make is about formal verification, coming back to the last point I made at the beginning about trustworthiness. So there is a whole area called continuous verification of neural networks, which essentially is interested in robustness properties of neural networks, so resistance to adversarial attacks. And what happens in there is that you break the training cycle by at each step of the training verified how are you doing with respect to a certain property, which for instance can be robustness. So how you encapsulate, how you describe the property you're interested in? Well, usually the people in that field use the loss function, and they use a specification language to describe this loss function. So they need different kind of layers to describe this thing. I think that if you use lenses, you are much better off, because first of all, this cycle here, it cries for a formalization in terms of lenses, because there is clearly a forward and a backward mode in this verify and retrain cycle. But I'm pretty sure some of you will see here an adjunction, abstract interpretation. There is lots here to be investigated in with our technology. Another point is also the specification language. We can do better, I think, because instead of having a layer, an overlay over our loss functions, we can let the loss functions be the specification language itself. At the end of the day, lenses are a rich formalism with many operations available. Loss functions are lenses. Let's use them as our specification language instead of coming up with a different logic to work on them. So that's the last direction I wanted to point. I will leave you to some pointers to implementations and some papers from which I've drawn this talk. Thanks.
All right, thank you, Fabio. So we have time for a couple of questions. Okay.
Thanks for your talk. I'll try to make them as brief as possible. The first one is, could you give me a little bit of perspective in terms of what are the contributions that thinking in terms of compositionality and lenses bring to, on the one hand, say modeling. So for instance, what does it add to the TensorFlow graph ecosystem, for instance? And secondly, you mentioned explainability. What's the, let's say, added value with respect to usual techniques like sensitivity analysis or these kind of things? Can we gain something more with respect to what doesn't use lenses?
So for your first question, I think this is basically suggesting different programming constructs that are typical than those that are typically used in TensorFlow. So to make some kind of analogy, I see TensorFlow more as imperative style of reasoning about these neural networks algorithms, where you have this tensor and transformation over them. Whereas in here, you focus more on processes that happen. So in a sense, I would say this is more functional style, whereas I see the primitives that TensorFlow gives you is more imperative style kind of language. And I think these can be very well integrated in TensorFlow. These, at the end of the day, are Python libraries. So it could offer simply other primitives to TensorFlow to design neural network algorithms, which I think can be more succinct. They can hide some of the complexity at times, which of course sometimes is desirable, sometimes is not, but it can have its merits. And I think this goes in a line of research that I've seen recently, about having functional programming to do automatic differentiation, for instance, to do various kinds of machine learning techniques. I think that is the same kind of spirit, more or less. We don't have yet, let's say, a implementation, a library that could compete with the TensorFlow thing, but I think this could be something to be looked into. And coming to the second question, in the explainability context, so I don't think at the present time this gives a really concrete case study for explainability. The idea is more that if you design your models, your algorithms using this kind of principles, is much easier to control how they are working, because you have these modules. So essentially, you have your work architecture is split into smaller parts. You can see the information flowing from each other. You can probably debug it more easily. So that's a bit of the advantage I see. So it's more like, let's say, from the design end of things. It's not something you can really apply when your model has been already built.
But I mean, in terms of, like, if we think of just a feed-forward neural network, the graph is super simple, and all the explainability is in the the way the training happens, right? That's the thing that's hard to explain some of the final results. So can you go beyond just representing the graph?
No, but this doesn't only represent the graph. This represents the training itself. So the training becomes the composition. So these various models, these various models, they are not just parts of the neural network. Some of them are actually, so they express the whole algorithm. There is nothing beyond that. They are the algorithm. So the algorithm, they become part, if you like, they become an extension of your network. Your network becomes not, your training is actually, I say, your network communicating with other networks, if you like. Each of them deputed to, for instance, doing the optimization process or so on. So that's the way I see it. As I'm saying, it's not yet, let's say, something that I can say gives a convincing answer to some of the explainability issues, but I think can be something that is useful to inform some of those approaches, especially those that look more at the design end of the training algorithms rather than the analysis of algorithms that already exist.
Other questions?
Thank you very much for the talk. I wanted to ask, so I know Bruno is very interested in this question, and I am too, but I never had your side of the picture. So your paper is called Categorical Foundation of Gradient-Based Learning because the things you showed us represent neural networks, but there are things in those categories that are non-neural networks, right? Do you have any idea how you could restrict this framework to capture exactly neural networks? So things where you have like matrix multiplying a vector, nonlinearity, bias, and let's go.
So yeah, something that I didn't mention, but definitely you can do, is to give a presentation by generators and relations to neural networks inside the category of smooth functions. So if you think about Boolean circuits, it's the same thing. You have this syntax that I showed before by this one. This syntax, okay, which tells you precisely what are the Boolean circuits. They are just the morphisms generated by these generating morphisms, okay? And you can do the same with neural networks. You can imagine of having some generating morphisms, and the neural networks are precisely the generated morphisms in this category. So the category, so some people smooth function somehow coincide, and of course you have maybe different neural networks representing the same function. What I think at the end of the day is you can use the generating morphism to represent morphism inside the category of smooth functions, and this will capture precisely your neural networks. And then it could be interesting to study, let's say, equivalences, because some neural networks, they do represent the same function, for instance. So that's something that is doable. I don't think it's done precisely or systematically anywhere, but I don't think it's too hard to do. And if you want a hint of how it's done, there is, for instance, a sketch in this paper called Backprop as a Functor. And they do it there somehow. I think that can be expanded into something that looks like that.
Okay, thank you.
Okay, so let us thank again Fabio.
Thank you.
Okay, and our next speaker is Francesco, so just give him a couple of minutes.
Francesco, scusami, l'ho caricato io, Danilo. Sì, in effetti si capiva.
Sì.
Hai vista?
Tutto schermo vista?
Schermo intero. Quello si vede anche su. Ecco. Fa vedere se funziona. Sì, è di... Porca vibra. Siamo sulla prima slide, relational.1. È quello grosso. Sì, schiaccia avanti e se schiaccia quello sotto va indietro. Yes. Così va indietro. Faccio il microfono. Tieni, pinzatelo come ritieni. Poi c'è questo affarotto che non so bene dove vuoi.
Sì. È acceso?
Dovrebbe essere acceso. Sì.
Does it work? Yeah.
Sì.
Okay.
Sì.
Sì.
Okay, so our next speaker is Francesco Dagnino from the University of Genova, and he will talk us about relational doctrines, monads, and Lax algebras. So, Francesco, please go.
Oh, thanks, Francesco, for the introduction. So, and thank you to the program committee for having me here. First of all, a disclaimer. So maybe during the talk I will be inconsistent with the slides. So please pay a lot of attention, and if I get inconsistent, stop me so that we can recover consistency. And so this talk is just I don't know, a collection of sparse ideas about relational stuff, and I think it's the result of a lot of discussions with many people, Francesco, Fabio, Pino, and some others I forgot. So it's nothing stable, it's just ongoing work. So any suggestion or criticism is more than welcome. So let's start from the very beginning. So in usually logic, in predicate logic, the basic notion is that of a predicate or a proposition of some sort, and basically unary predicates. So you represent, from a semantic perspective, they can be thought of as subset of a given set. And you can talk about relations if you allow yourself to have more than one variable, and then you take a formula over this context with many variables, and this is a relation. And you can define relational constructs in terms of first-order connectives, basically. So the composition, you can define the relation, the composition of binary relation as by an existential quantification and a conjunction. This is standard stuff. But there is another approach to logic, which is, let's say, relational calculus or relational logic, where instead the primitive concepts are binary relations themselves, and where all relational constructs are taken as primitive logical operations instead of being derived from the first-order connectives. And the main one are, let's say, relational composition, identity, the converse, and then usually some Boolean operations, which are the standard ones. And this has some advantages because you get a complete variable-free language where you do not need really individual variables in this setting. And that's nice because it is more suited when you have to move from the standard logic to more quantitative or substructural setting, where having compound contexts with many variables is something which is quite difficult to handle. And moreover, it is less expressive than usual first-order logic, but is still quite expressive. And as we will see, I hope, it allows us to do many things. So from a categorical point of view, to do relational stuff, the usual setups are, let's say, allegories or Cartesian by categories are two different things, of course, but roughly these are categories enriched over posets with some additional structure. They are quite natural and works very well, but let's say they have a lot logical principles which are implicit and which are there under the hood, especially some choice rules, which maybe one do not like, especially if you want to be constructive. So in usual predicate logics, to avoid this and really separate the logic and the algebraic part, one moves to a fibered setting, and doctrines are a very simple fibered setting, which nevertheless are quite expressive and useful. So the goal of this talk is hopefully to show you how doctrines can be used to do relational reasoning, or let's say to do relational logic, and see some applications to, let's say, Lax algebras. This is the outline of the talk. So I will first introduce relational doctrines, then I will show you several examples, and some basic properties. And finally, I will discuss monads and the construction of Lax algebras on these kind of doctrines. Sorry, maybe I am inconsistent in the moment at this time. So that's the definition of doctrines, right?
Yes.
Yeah. So sorry. So doctrines are just contravariant functors, as you can see, from a category to the category of posets. And the intuition is that the base category models, as I said, the algebraic part, so objects we are interested in and transformations between them. And every fiber, so every poset above every object in the base category can be thought of as the poset of predicate on that object ordered by logical entailments. And the action on morphisms of the base category is instead substitution. And one usually requires the base category to have finite products in order to allow for many variables. So as I was saying, this is the goal, right? Yes. And this is the outline, exactly. Right. So I have already discussed this. So have you any questions so far before I move on? Okay. Relational doctrines. So to define relational doctrines, I would need a base category, so the object and the transformation I want, and a relation between such objects and their basic structure. And in this talk, I will just focus on relational composition and identities for simplicity. So what is a relational doctrine? So we have a base category to model our objects, and a contravariant functor from the product of the category with itself to the category of posets. And this models for each pair of objects the poset of relations ordered by some kind of logical entailment. And the action on pairs of morphisms represent reindexing, so substitution in a sense. Okay, then I have to define identities. And relational identities are just a family of objects in the fiber over A and A. So an identity relation is a relation from A to itself. And we require this family to be to satisfy this Lax naturality condition, let's say. Basically, we require each arrow in the base category to preserve identity relations. That's pretty standard. So basically, this says that an arrow maps equal elements to equal elements, roughly. Okay, then we have relational composition, and that's, again, pretty simple. So we require, we take three objects, and we require a family of monotone maps from relation from A to B times relation from B to C to relation from A to C. And so which is monotone, so preserve the order. And moreover, we require, again, this Lax naturality condition. So this says that if we first reindex along F and G, the first relation, and then we reindex along G and H, the second relation, and then we compose, we get something which is smaller than doing first the relational composition and then reindex along F and H. So notice that here the middle arrow disappears. And moreover, we require the usual equational axioms for relational composition and identity. So relational composition is associative, and the identity relation is the neutral element. Okay, fair enough. These are relational doctrines, pretty simple. But let's have a more structured perspective on this. So to do so, I need to introduce morphisms between doctrines. So a morphism between two doctrines P and Q is just a pair of a functor between the base categories of the two doctrines and a natural transformation which lifts a predicate over an object in the first category to a predicate or in the second doctrine over the action of the functor on on that object. So it goes from P of X to Q of F of X, basically. And we require this to be lax natural. This is something for those of you who are used to work with doctrines, which is a bit unusual, because usually this is the second component is a strict natural transformation. But here we really need lax naturality, and I think we will see at some point the reason why. But basically, yeah, maybe it's in the next slide. And so this is the morphisms of doctrines, and given that, we can describe the structure of a relational doctrines as algebraic structure inside the category of doctrines, basically. So what is the identity? It's just a morphism from the doctrine, the trivial doctrine, basically, which maps every object in C to the singleton poset, to the doctrine, to our doctrine of relations, which has as a functor between base categories the diagonal functor, which says that we want the identity relation to be a relation with the same domain and codomain. And the fact that the domain is the trivial doctrine means that we pick one element in all these fibers, basically. And the lax naturality models the fact that we only want arrows to preserve identity relations and not to, let's say, reflex. If this transformation is strictly natural, this basically means that every arrow in the base category is injective, because we have also the other direction. So if f of x is equal to f of y, then x is equal to y, which is not which is a bit strange, I think. So that's the point for the identity. And for composition, we have to consider this pullbacks with pullback. So we have basically projections from our doctrine of relations to the trivial doctrine, which projects on the first, on the second component, on the base categories, and which trivializes the relations. So it's the terminal arrow, basically. And we do this pullback, and so the result, which is R2, is a doctrine which has as base category the product of 3 copies of C, and the fiber over A, B, and C is the product of relations from A to B and relations from B to C, basically. And then relational composition is just an arrow from this pullback to the doctrine of relation, which has the first and the third projection as base functor. And with our equational axioms, what we get basically is that this stuff gives us an internal category to the category of doctrine. So this is some kind of more structured definition of what relational doctrine is. Questions so far? Okay. So let's see some examples. So the first one are quantile valued relations. So the base category is set. We fix a quantile, which is a complete lattice with a monoidal operation which distributes over arbitrary joints. And relations are just functions. Relations from A to B are functions from the product of A and B to the underlying set of the quantile with the pointwise order. And reindexing is given by precomposition. So here the identity relation is the function which maps to the unit of the quantile if the two elements are equal, and to the bottom element if the two elements are different. And the relational composition is given by taking this sup, this join, basically, of the monoidal product of the two relations. So these examples cover many usual examples in relational reasoning. So here we have standard relation, metric relations, modal relations, and many others. And actually, this stuff can be generalized to an arbitrary elementary existential primary linear doctrine, elementary and existential linear doctrine, which is a doctrine modeling a fragment of linear logic enriched with the existential quantification and usual equality. Okay, so here we have another examples, which are matrices. So if we take an ordered semi-ring and we can define we can consider the category of finite sets with all their functions. And the doctrine is similar to the previous one. So maps, so relations from A to B are maps from the product to the underlying set of the semi-ring with the pointwise order and precomposition as reindexing. So here the identity is the Kronecker delta, basically. And relational composition is given by matrix multiplication, basically. Notice that that sum is finite because we are working with finite sets. And we can extend all this stuff also to arbitrary sets in a couple of ways. Maybe we can discuss it afterwards if you're interested. Okay, so another example are spans inside the category with weak pullbacks. And so here the order between spans is the usual one. So we say that a span is smaller than another if there exists an arrow which makes the two triangle, an arrow between the vertices which makes the two triangle commute. And precomposition is given by, reindexing is given by weak pullbacks. The identity is the identity span, and the relational composition is the usual composition of span. Oh, sorry, there is, of course, a poset reflection there in the definition of the fibers because we have just weak pullbacks, and so we need to, so that is just a full partial order. Finally, if we take a category enriched over posets, we can define in the standard way the category of maps in this C, where the objects are the same, and the arrows are basically adjunctions inside the category C in the direction of the left adjoints. This basically models, let's say, functional relations inside that post-enriched function, post-enriched category. And then we can define a relational doctrine where the base category is the category of maps, and the fibers, the relation are all the arrows in the category C. And so relational composition is the composition of C, and reindexing is given by that weird composition. So we first pre-compose with the left adjoint, and we post-compose with the right adjoint, a relation R, which is an arrow. Okay. Now, what can we do with a relational doctrine? This is just useful for the next slide. So we can define graphs of arrows in the base category. So we can represent basically arrows as spatial relations. And the definition is that one. So we just apply the reindexing along the arrow and the identity to the identity relation. And this gives us a relation from A to B, given an arrow F from A to B. And what we can also do is to get a converse of this relation, which is just obtained by reindexing in the other, swapping the two arrows, basically. And the nice thing is that these two inequalities holds, which basically says that the graph of an arrow in the base category is a functional and total relation in the relational doctrine. So it's really a function. And last, using graphs, we can encode reindexing by means of relational composition in that way. So we pre-compose with F, and we post-compose with the converse of G for reindexing. But we also discover that we have all left adjoints to this reindexing, just doing the relational composition in the other direction. And this basically means that we not only have reindexing, but we also have images along all arrows in the base category. Okay. Monads. So the last part is about Lax algebras and monads on relational doctrines. So to define monads on relational doctrines, I first need to define a suitable two category of this stuff. That's, again, pretty standard. So the objects are relational doctrines. One arrows consist of a functor between the base category and a lax natural transformation between the doctrines of relations. And notice that these basically are usual relators or lax extension of functors for those of you who are used to relational stuff. And two arrows are just the natural transformations between the underlying functors of the one arrow, which has to satisfy that usual inequality that basically says that these natural transformations respect the second component of the one arrow. Of course, this is important. We require the second component of one arrows to preserve relational composition and identities in a strict way. This is not very usual for relational liftings because they require to preserve composition and identities in a lax way. But in this setting, it's better to work in this way because otherwise there are some compositions which fail in the category of monads. Okay, so this is the two category, and we can consider monads inside these two category. And this is the definition spelled out, basically, and is the same thing of a relational extension of a monad, again, for those of you who are used with relational stuff. And for those of you who are used to category theory, it's just a monad inside the two category of doctrines, so nothing interesting. But let me remark this, because the construction of spans I showed you, which is again pretty standard, nothing very new, extends to a two-functor from the category of categories from the two category of categories with weak pullbacks and weak pullbacks preserving functors to the two category of relational doctrines. And so these two functors maps monads to monads, and basically these realize the well-known bar extensions of monads in an abstract setting, basically. Okay, lax algebras, and then I conclude. How much time do I have?
5 minutes.
Okay, I hope I will finish. So we take a relational doctrine and a monad on it, and we want to construct a category of lax algebras. So basically, this follows what people working on monoidal topology do. They work basically on a category of sets. Here we work on an arbitrary relational doctrine. So given this monad, we define this category of lax algebras where objects are pairs of an object in the base category and a relation from T of X to X, right? Or T of A to A, I don't remember. From T of A to A, and which has to satisfy a couple of inequalities, which are, if you look at it, look at them, they are the usual axiom for an algebra for a monad, but expressed in a lax way, so with an inequality instead of an equality. And this is possible because we are working with relations and not just with arrows. And morphisms are just arrows between the carriers of the algebras, which has to preserve the algebra, which is given by the relation. So again, this is the same thing as a homomorphism between usual algebras, but here again it is not strict but lax, because we only want relations to be preserved and not to be reflected in a sense. And okay, and then we can define a doctrine on this in a pretty simple way. So we take relations between two algebras to be all the relations between their underlying objects. And that's it. So the rest of the structure is the same of the original doctrine. And as people working on monoidal topology showed, these constructions covers many examples, which are pretty usual in mathematics, like preorder set, Liouville metric spaces, topological spaces, and all this stuff are instances of this construction. And what we can prove is that this construction has a similar property to the Eilenberg-Moore construction, which is given by this equivalence, this isomorphism between home categories, where the home category on the left is the home category in the category of in the two category of relational doctrines, while on the right we have the home category of the two category of monads. But this is not the usual two category of monads, because we have to fill, there is a difference in monads morphism, because our notion of algebras are not arrows in the base category, but is a relational notion of algebra. And so we need to fill the squares of monads morphisms by a family of relations and not by a natural transformation, which has to satisfy a bunch of axioms. I have not time to go into the details, but are what you expect, I think, and what is needed to make the isomorphism work, basically. So that's it. There is a lot of things which are open, so probably this is just a first step towards working with doctrines and relational stuff. What I would like to do in the future is to really use these things to reason about more sophisticated things like choice rules or quotients and this kind of stuff in a purely relational way. So without using products or existential quantification, but just using relational stuff. So thank you for the attention.
All right, so thank you, Francesco. Questions?
Thanks a lot for the very nice talk. I missed one point, but when you do the construction of maps, this allow you to move from a relational doctrine to a traditional doctrine, or
No, I do the construction of maps because I need a base category to identify, let's say, the algebraic part, and I need to define the reindexing along arrows in the base category. And if you remember the definition, to define that reindexing, I need the right adjoint. So I cannot take the full Poisson-Rich category as base category of the relational doctrine, because in that setting, not all arrows are adjoints. And so I could not define the reindexing part. Basically, I split the logic of relations and the algebraic part where we have objects and transformations between them, which are functional relations, basically. I don't know if I answered.
This was clear to me. Okay, but maybe you can always reduce a relational doctrine to an existential one, because somehow.
No, because I do not have products in the base category. So to get an existential doctrine, I need to have products, because as I said at the beginning, I need to. So basically, working with existential doctrines is like talking about relations in a predicate logic. And so to do this, I need to have many variables. And to have many variables, I need products in the base category.
Okay.
And that's what I would like to avoid, because, for instance, working in a quantitative setting, what you usually get in the base category is just a monoidal product and not a Cartesian product, and so having existential quantifiers becomes difficult.
Okay, but so as soon as you have a Cartesian product, you end up into the relational doctrine may collapse with the.
That's a point for future work. I need to. I think I also need some kind of binary connective on the fibers. Okay. At least a tensor, so a linear conjunction. to get back an existential doctrine.
Thanks a lot.
Also, just a few not if I have time, one more comment on this. I'm aware of a paper which relates Cartesian bicategories and existential elementary doctrines, and the point there is to get the equivalence, you need existential doctrines with a rule of choice. While if you work with relational doctrines, probably, because I have to check these details we were discussing, you get an equivalence with existential doctrines not necessarily having the rule of unique choice, as in Cartesian bicategories.
I have a question, maybe perhaps related to Filippo's. So if you forget about the hypothesis of the base category having products, do you expect relational doctrines to have some kind of universal property among doctrines? Or I mean, can you imagine some monad or something such that they are coalgebras for a monad or something like that?
So they are categories, they are internal categories. So I'm not really, I'm a computer scientist, I'm not really expert on all these details, but maybe that internal categories are algebras or not. At least I think they are models for a sketch.
Yes, I think so too.
And so we characterize in that way, I think.
All right, thanks.
Okay, I think we are done and almost in time. So let us thank again Francesco. And now we have the coffee break, so we will meet again here in a few minutes, actually. Grazie. Mi ricordo, c'è coffee break? Ma
Okay. So welcome everybody. So the first speaker of this session is Guglielmo Nocera, who will give us a Amarcord Blackboard talk on the exodomy theorem.
Yes. Online? Okay. Grazie. Okay, thank you so much for the invitation. Actually, the first time I was honored to give a talk at ItaCa was last year. And what I did last time is same thing I will do this time. Not the same content, of course, but the same strategy. So unfortunately, I don't really work in category theory. So what I did is take something from my research field. Notice that I used something in category theory, some categorical theoretic result to prove something, and talk about that. And of course, that's not a result of mine. So at the end, I will try to explain how that result somehow enters into my work. Good. So the title of the talk, let's try to do, is this a good, funziona come altezza? Okay. Title of the talk is the exodromy theorem and an application. So let us recall the following thing. So the base object in this discussion will be X, a topological space. Good. So definition, the category of presheaves over a topological space is defined as the category of functors from the category of open subsets of X to the category of sets. Good. What we'll do is to study some subcategories of this, so namely presheaves or sheaves with certain properties, and ask ourselves a particular question, which will come in a moment. So for example, so setting, so let X be a topological space, and suppose you have extra datum, extra structure. I will be more precise later. Now I'm just trying to converge to what I want. So for now, extra datum means mathematically nothing. Like, for example, what? So the datum of a closed subset. This is extra datum with respect to the original thing. Or what is called a stratification. Stratification is in some sense a generalization of this. So it's a system, a partition of your topological space into smaller spaces. Again, I will give the definition later. Or other things, a group action, so extra datum. What we will be interested in is this one. And then what can you do? You can do the following. You can consider, so you can consider sheaves or presheaves on X with a certain property which, to be stated, needs such a datum. So, for example, sheaves with support in Z, or sheaves which are locally constant on X. There's no extra structure here. Or sheaves which are constructible over the stratification. These are the examples I'm interested in, and I will give definitions in a precise way later. So, examples, sheaves with support in Z, meaning that they are zero outside of Z, or what are called constructible sheaves, or equivariant sheaves with respect to some action as well. So categorically, what we are doing is just considering a subcategory of this, where the property that cuts out the subcategory is, okay, to satisfy the scent, for example, that gives you a sheaf, plus to be constructible as many other properties. So we end up with something of this kind. P is your property. So one of these. X is your space. S is my extra datum. And, well, you may also have a category of coefficients which generalizes this. So variation of this definition, so presheaves of X with coefficients in B, if B is a category. This is just functors from open of X to B. Just this. Okay, this was just an introductory part to give you the flavor of the kind of thing we're interested in. And to conclude this introductory part, the question. So what do I want to do with these subcategories? So question. Are there any cases of these geometrically relevant examples where this kind of thing, so presheaves with this very vague property, very undetermined property, with coefficients in this category, can I express this category in a way that resembles the bigger one? By this, I mean as a category of functors, where the target category is again B, and the source category is something else, something which is, of course, not open of X, is something more sophisticated, because it has to take into account the structure and the property, and which I will denote by X, A of X as P. So it's a new category that depends. But as you can see, this is non-trivial. So not every subcategory of a category of pre-sheaves may be expressed as follows, at least in principle, because I am requiring that B stays the same. So I don't want the coefficients to depend on the original geometric datum, exactly as it's happening here. Sorry. Okay. This may seem like a vague question, but I think it will become clear later. And before diving into the theorems, let me just say one possible advantage of such a description, and a second advantage I will give at the end of the talk. So advantage of this. So why would I be interested in expressing a category of sheaves with some properties, again, in this form?
Sorry, can I stop you for a second?
Sure.
We want this, assume you have a solution to this problem. Assume you have a solution to this problem. You want this to be natural in B,
Yes.
or is it too strong?
You mean in B?
In B, yes.
Yeah, in B it's okay, but the real thing, which is not trivial, is also A to be natural in X as P in some way.
Of course, yes.
Actually,
Okay.
P is fixed, but in XS, yes.
Okay.
I will give an example. I think
Okay,
it will answer your question. But yes, everything would like to be natural, and the advantages I'm going to show, especially the second one, will take advantage of this naturality.
Mhm.
So yes, the question is perfectly fits perfectly in the setting.
Thanks.
And so yeah, the first advantage is that if B is, say, presentable, or something completely different, abelian, so an abelian category, or what is called a stable infinity category, which doesn't really, it's not of interest to us here, but so many possible important properties. Well, then, under the possible assumption, at least in this case, it's important that A is small, but usually everything is small in these kind of contexts. But then also our thing is, so also this category of pre-sheaves is if the answer is true, so also the category of functors. This is not completely obvious. And in general, it's not obvious how to prove such a statement, so that this thing is presentable, this thing is stable, and so on, if one doesn't have such a presentation. In particular, in the case of constructible sheaves, which I didn't define yet, but it's the case I'm interested in. Sorry, the way I convinced myself that it was presentable and it was stable in the stable case, and so on, was exactly this way. And there is also another application, which I will be more precise about that later, symmetric monoidality. So is the association XS going to this category in any way symmetric monoidal? This is interesting, actually. And so if I have the product of two topological spaces with two structures, how does it convert into, how does this kind of thing split into the two partial data of what I need? And in the case I needed, the answer was yes, thanks to this co-representability result. Good, so let us move to the actual part of the thing. So first example, first of two. local systems. So let X be a connected topological space. A local system on X is a sheaf. So it's a presheaf with the usual topology, so the topology of the space. Oh, sorry, for example, here I could have added a Grothendieck topology. This would be another extra structure with respect to which I can ask some properties to be true. So a local system on X is a sheaf over X, which is locally constant. Okay, that's the definition. I will try to write in the upper part of this. So the theorem related to this example is the following. The category of local systems over X, so this is defined as having as objects such sheaves, as morphisms of sheaves. And how does it compare to what we were saying? Well, S, there is no S here. There's just a space. But there is a P. P is exactly to be locally constant. So I'm considering, and also to have descent, so to be sheaves, not just pre-sheaves. Okay, so I'm considering the subcategory of this, full subcategory spanned by those objects which are sheaves and also are locally constant. So this is my category. This is equivalent as a category to something of that kind, and in particular to what are called the representations of the fundamental group of X, which I will denote by this. Okay, where this thing, I1 of X, as a category, this is a category, is defined as having as objects only one point, and as morphisms, so hom between the point and itself, is pi1 of X, the fundamental group, and composition is exactly multiplication, the usual thing you do with groups. Okay, and this is a result in topology that goes in that direction, right? Because the category A here depends on X, but the target category doesn't. It's actually the original category of coefficients. And actually, this can also be generalized to other categories of coefficients, for example, abelian groups or vector spaces. Okay, this is somehow a baby example. There's no S. This is what makes it more trivial in some sense. Huh. Okay. In the non-connected case, so when X is not connected, what appears here is the so-called fundamental group point. Now, let's move to the last part of the talk, constructible sheaves. So constructible sheaves are a generalization of what I called local systems, of locally constant sheaves. Let's give the definition. So definition, first part of the definition is what is a stratification? So X, topological space. A stratification of X is a decomposition. So it's a family of Zi, with I belonging to some set of indices I. Each of one is a subset of X, which is locally closed. Sorry for so much topology. And Okay, these are a partition of X, so their union is so they are all disjoint, and their union is exactly X. Plus, there is some condition called condition of the frontier that I have to state. So essentially, for each I, the closure of I as a subspace is a union of strata, where those are the strata. So these are called, each one of these is called stratum. Okay, just forget it if you don't care. Okay, this is called a stratification. It's a partition, but it's a special kind of partition. Then I can define a constructible sheaf over X. So F sheaf over X, perhaps should, is called constructible if the restriction of F to each one of these things, the strata, so this is the picture, topological space partitioned in some smaller subsets. So the restriction to each one of these is locally constant. So it's a local system. So take the trivial stratification with only one subset, which is the whole space, and you get the previous definition. Okay, these sheaves form a full subcategory of the category of pre-sheaves over your space. And you may ask the usual question. So is this subcategory co-representable as such a thing? Again, in this case, B is the category of sets, but you can generalize this. It's not important now. And the answer is yes, which is the main thing I wanted to tell you today. Okay, let me just do this. So the exodromy theorem, I mean, today it's called the exodromy theorem. Actually, the actual exodromy theorem is a vast generalization of this, but so the theorem is that if, let me call the stratification S. Stratification S is this family. And it's the same letter I had used here. So it's the actual additional datum I am putting on my topological space. So if S is has some nice properties, so additional to the one I stated there, it's called conical stratification. It's not important here to specify what this means. Of course, you can ask questions. So if S is nice properties, then there exists such an A access P, so it's called the category of exit paths associated to S, X and S. The P is implicit. I mean, I construct this because I want to deal with constructible sheaves, such that the category of constructible sheaves over X with respect to the stratification S, in the sense of that definition, is equivalent as a category as to fun exit XS set. Okay, so this is actually the basic formulation of this thing. The original proof that is not in this setting. It's in the, let me say, it's in the derived setting, but this is what interests us now. And that's a result going essentially in this direction, because it's exactly that kind of representation. Let me just conclude with the application. So what was the second advantage I was mentioning before? Well, you may take products of such stratified spaces. So it's like considering the Cartesian monoidal structure on topological spaces, but somehow lifting it to the category of stratified topological spaces. So you have a category of stratified topological spaces, just meaning a topological space with such a stratification. And you can take products of those. So you actually have a Cartesian structure. Then you can associate to such a pair, XS, this thing, constructible sheaves over XS. This is a category. It's convenient to see it as a presentable. And in particular, it's going to live in the symmetric monoidal category of presentable categories with the tensor product, the co-complete tensor product. Okay. So one may ask, is this association symmetric monoidal? Well, if you are if you restrict here to conical stratifications, so if you are in this situation, then it's true. And for example, what a collaborator of mine and I proved, usual partner in crime for these things, is that the so-called Whitney stratifications fit into this context. Actually, that was previously known, but what we did is something a bit more sophisticated, but it goes in that direction. And the answer is yes, you can actually prove thanks to this thing. It's not completely obvious because you have to inspect how A works with respect to symmetric monoidality, and then you have to work with the notion of pre-sheaf. But you can then prove that this is actually symmetric monoidal. And this was something I really, really, really needed for my research, because I wanted to transport a monoidal structure, an algebra structure for my space in the stratified setting to the category. And if this is symmetric monoidal, Lex monoidal would suffice. You can transport an algebra structure here to here, which is what I needed for reasons I cannot expand now. Thanks.
Thank you. Is there any question?
Hi, thanks for your talk. So I guess we can think of locally constant sheaves as coverings of the topological space, right? And can I think of the exit paths category as some sort of gluing of the pi1 of the spaces in the stratification?
Yeah, actually, the symbol you use to denote exit, so Lurie used the symbol sing SX, meaning that it's actually some kind of generalization of the singular complex, so the list of essentially all homotopy groups. But of course, the stratification has to play a role there, right? It's the homotopy groups just don't see anything of the stratification. So the analog you're looking for is you replace paths, which are the thing that give you the fundamental group, with what are called the exit paths. So exit paths are paths that somehow play with the stratification. So exit means that they have to, where's the thing? So you replace the notion of path, which is gamma from I to X, which gives you the fundamental group, with gamma from I to X, such that for every, so if 0 goes to some stratum, then whenever the path exits, cannot come back. Where exits means go to, let me say, a higher dimensional stratum. It's not the correct notion, but that's it. So suppose you stratify with a line or a curve plus the complement. This is the small stratum, this is the big stratum, so your path has to go away. But to come back to your question, I think this is the actual analogy you use. So you mentioned the word gluing. I'm not sure I can interpret that, but at least
maybe I can justify my intuition. So you have your categorical constructible sheaves, right?
Yes.
And by restriction, you can project over the local systems of each stratum.
Mm-hmm, sure.
So if you think of it, let's say,
I see.
representably, then you get, well, I mean, you don't necessarily get those because...
No, now I got it, sorry.
Yeah.
Yes. No, yeah, the gluing you're referring to is some is related to the following problem. You have a decomposition of your space, not into two open sets, that would be, well, not a covering of open set, that would be gluing, but you have an actual decomposition in a closed subset and an open subset. So the fake gluing you would like to have in this thing is, I think, is called recall mum. And that's the answer to your question. Yes, it's related to this kind of problem, and it's a gluing of your data on the closed one and the open one, or on the stratification in the general case.
Okay, thanks.
Hi. On the properties, can you ask something about the geometry X? I don't know. Not
What,
just
what?
Among the properties, can you ask the extra datum?
Okay, yes.
Can you, I mean, does this give you something stronger when you X is some, I don't know, a complex variety? For instance,
Okay. So you mean for one of these particular settings, or in general?
Yeah, I don't know, because for instance, local systems are become very interesting by the Riemann-Hilbert correspondence, and
Okay.
so I would imagine.
Yeah, I don't know if for example, the Riemann-Hilbert correspondence for constructible sheaves, for example, benefits in any way of this exodromy representation. We both know whom to ask, but I'm not sure. Maybe there is some simplification of things, not that I know of, but I may be wrong.
Okay, I think there is no time for other questions, so let's thank the speaker again. So the next speaker is Matteo Spadetto. We'll talk about a result, a conservative-like result in a propositional type theory. Oh, no, this is not necessary.
How does it work? Okay. Qui, vero? Ah no, qua. Benone. Okay. Thanks, Samuele, for the introduction. Thanks to all of the organizers for doing this event for us. And of course, thanks to all of you for listening to this talk. As Samuele said, today we talk about conservativity. So first thing to do, let us recall what conservativity is, at least in the framework of dependent type theories. So suppose that we are given two dependent type theories, T1 and T2. And let us assume that the rules of T1, so the inference rules, the type constructors of T1, are contained in T2. But let us assume that they do not coincide, so that there are actually some judgments that T2 infers and that the T1 is not able to prove. Okay, even in this situation, we can still ask ourselves whether the two theories prove the same statements. So if you interpret the types of a dependent type theory as a statements, and the terms of these types as proofs of the statement, then this property corresponds to asking that, to the property that the theory T1 considers a given type, capital T, inhabited as long as it is inhabited according to T2. So in other words, if T2 proves a term judgment A lives in T, then T1 proves the same thing. So it also finds it is also able to build a term, let us call it A tilde, that lives in T. When this happens, we say that T2 is conservative over T1. So meaning that, I guess, if you reinforce the rules of T1 by the rules of T2, you do not risk to modify, namely to increase the deductive power of T1. You can assume you're working in T1, use the rules of T2, and still get results that are true in T1. So for instance, a conservativity result that appears in the literature is the following. T2 is an extensional type theory, and the T1 is an intensional type theory with some fundamental extensional assumptions, like for instance that any loop P is propositionally a reflexivity. With these two theories, you actually have a conservativity result. T2 is conservative over T1. And the proof is contained in this work by Hoffman of 1996, over which this talk is based. In fact, in this talk, we consider T1 to be an even farther weakening of the intensional type theory. Namely, we assume that T1 has propositional ID types that now we will talk about. Briefly, without going through the rules. Intensional ID types that we all know. These are the ID types of Per-Martin-Löf dependent type theory. There is a formation rule. When you have two terms of the same type, you can form their ID type. You have an introduction rule. If you plug in the same variable in both hand sides, then there's a choice of a term R of X. There's a path elimination rule that tells us that if we are given a statement, capital C, depending on a general path, and if we have a proof of that statement C, so a term that here I call Q of X, for C in case where P is a reflexivity, then you actually have a proof that here I call J for the general statement. So for the statement C dependent on a general path P. And the computation rule tells us that this new proof J coincides with the one in the hypothesis Q if in place of P you plug in the reflexivity. What do we do today? We do not require the computation rule to be strict, to be a judgmental identification of two terms. But we require something less, okay? So in place of the judgmental ruling, in place of the computation rule in judgmental form, we just require its propositional weak version, that is that there is some term that inhabits the corresponding ID type. This is what we require. These are the propositional ID types. We require that they exist in our type theory. ID types were considered, for instance, in 2014, in a cubical setting. These authors were trying to produce a model of Per-Martin-Löf dependent type theory. And in this case, there was no way of making the judgmental rule of the ID, of making the computation rule of the ID types strict. It only appeared in propositional form. Then there's this very important work by Benno van den Berg, in which he produces a notion of semantics for propositional identity types, which is based on this notion of path category. And more recently, Raphael Bouquet was interested in comparing type theories having weak equalities, so propositional equalities, to the corresponding type theories having strict equalities. So this was just a survey on where propositional ID types appear in the literature. In a similar flavor, we can consider the same form of weakening for, but here I guess you do not see the last line. Okay, this is, anyways, no worries. Propositional dependent sum types, thanks Samuele. Dependent sum types also have a computational rule, right? And again, we do not require, in this case, to have it in judgmental form. We just require it in a weaker form, that there is a term that inhabits the corresponding ID type. So now we can state the aim of the talk. we let PTT, for propositional type theory, to be a dependent type theory with propositional ID types, propositional sigma types, and propositional pi types. And our aim is to compare it to extensional type theories, looking for a conservativity result. The argument is completely semantical, and in detail we use the soundness of the semantics provided by the notion of category with attributes. Even though any other, I'm pretty sure that any other semantics would have worked as well. So if you prefer to use natural models, comprehension categories, I guess the same argument can be adapted. Now I would like to state the result before briefly going through the proof. And in order to do this, I need to introduce the following notion, the notion of simple type. We say that a type judgment, capital T, of PTT, is simple if it belongs to the smallest family, curly f, of type judgments of PTT, closed by the following clauses. The first one is that all the basic type judgments of PTT, which are H sets, which happen to be H sets, need to belong to F. And the second condition is that the family is closed up to the formation rules of id, pi, and sigma. So basically, you consider the simple types, the simple basic types, the basic H side, again, the basic H sets of PTT, okay? And you close them by equality, dependent product, and the dependent sum. What you get are the simple types. Now, let us consider finally an extensional type theory, which we build in the following way. Okay, we will call it ETT. At first, let us say which are the basic types of ETT. These are just the basic H sets of PTT. So we consider an extensional type theory having a basic type, so a type which is not given by type constructors, an axiom, for any basic H set of PTT. And the same for basic terms. If we have a basic term living in a basic H set of PTT, then we require it to exist even in our extensional type theory. Okay? So basically, this is the extensional type theory generated by the axioms, by the simple axioms of PTT, simple types of PTT, and the simple basic terms in these simple basic types. And now we can actually interpret ETT, which we can actually interpret the simple type judgments of PTT inside ETT. We can interpret the simple context, the simple type judgments in simple contexts, and the term judgments of PTT of some simple type in simple context. Let us call these 3 points the simple fragment of PTT from now on. So what is the simple fragment of PTT? It's just the simple types, the simple context of PTT, the simple types of PTT, and the terms living in some simple type of PTT. This is for this fragment of PTT, you can define an interpretation in ETT, which we denote as a module. Then the result is that ETT is conservative over PTT relative to this family of simple types, meaning that if we are given a simple context gamma of PTT and a simple type, capital T, in this simple context, assuming that ETT proves the interpretation of T, so assuming that ETT is able to build some term A in the interpretation of T, then so does PTT. PTT infers that there is a term, let us call it A tilde in T. And moreover, once you interpret A tilde in ETT, then ETT is not able to distinguish it from the term that ETT provides. So basically, it doesn't distinguish between the given proof and the proof that PTT provides. So let us briefly make this out. What does it mean? It means that despite PTT is actually weaker than ETT, because there are things that ETT proves and PTT doesn't, there is an interesting family of type judgments, namely the simple ones, where the two theories have the same power. Okay, and one can argue that this is a bit informal. What I'm saying is informal, but one can argue that simple types is what really matters in a dependent type theory. Why? Because in a dependent type theoretic foundation, when you do concrete mathematics, constructive real analysis, whatever, you only care about H sets. Like R is provably an H set, or I don't know, if you want to do abstract algebra, then the carrier types are all H sets, and most of the properties that you want to prove can be stated as H sets. And the simple types are not all of the H sets, because okay, for sure, simple types you can prove by induction on their complexity that they are all H sets. Usually, there are in a dependent type theory there are also some H sets which are not simple types. But we can say that most of the H sets that one cares about are simple types. In particular, if PTT, here we are working very generally. PTT has a very general family of basic types. But you know that in order to have a foundation of constructive mathematics, you only need 3 of them, maybe 4. Yeah, 4. You need the empty type, the singleton type, the number 2, and the natural numbers object. This is enough. Well, if PTT has only these 4 simple types, only these 4 basic types, these are provably H sets in PTT. So in this case, which is enough to give a foundation of constructive mathematics, in this case, PTT only has H sets as basic types. And so in this case, it would have a full conservativity, because there's no distinction between basic types and basic types which are H sets. Any basic types is an H set. So in that case, you would have a full conservativity result. Okay, this was to briefly comment this result, what it can be useful for. And now I would like in the remainder to briefly go through the proof without entering too much through the details. So in this case, I decided to use the notion of a category with attributes to provide a notion of semantics for extensional and propositional type theories. Greta this morning already told us how the semantics works, but in the framework of categories with families of display maps, but nothing really changes. The idea is that what is a category with attributes? You are given a category C, whose objects we call semantic contexts, right? Gamma, delta, and so on. Then you want to give semantic types in this context. So you are given a pre-sheaf TP, which sends any context gamma into the family of its semantic types, which I denote with capital Latin letters, A, B, so on. Then you you can extend the context with types in that context, right? Semantic context extension. And then you are given a family of display maps, which is natural from the semantic context extension to the growth and deconstruction associated to TP. And moreover, it's not just required to be natural, but it is also required to be Cartesian. This is very important to model a strict notion of substitution. In line structure, we define the semantic terms of a given semantic type A to be the sections of the corresponding display map. Because, as we saw even this morning, in the syntax of a dependent type theory, the terms of a given type are in bijection with the sections of the corresponding display map. So now we do exactly this thing. We define them to be the sections of the display maps. Categories with attributes are models of dependent type theories. Because if you are given, you can really extend the substitution to terms. If you are given a section A of a given display map, PA, so a semantic term A of a term of a type capital A, then there is unique A section of a PAF making the upper square commute. And we define A of F to be the substitution of a given morphism of context F inside the term A. So in this way, you, up to defining how to interpret any judgment of a dependent type theory, one can prove that this notion of substitution models all of the rules of the substitution of Per Martin-Löf dependent type theory. So this provides a notion of sound semantics for any dependent type theory, up to giving a choice of the basic types and the basic terms. And of course, you can specialize this notion of semantics to provide semantics for extensional, intensional, propositional type theories. You just need to specify some choices of semantic types and semantic terms in such a way that the type constructors that you need are modeled. So now I can talk about the proof strategy in a few minutes. The idea is that you exhibit a model M of ETT, okay? And of course, if it is a model of ETT, it is also a model of the simple fragment of PTT. Because any model of an extensional type theory is also a model of a propositional type theory. It is also a very special one. So you consider a model M of ETT, okay? And you would like it to be to have the following property with respect to the simple fragment of PTT. We want that the interpretation of the simple fragment of PTT inside this model is surjective, okay? So that what would we like? That any semantic context of M is the image of some simple context of PTT. That any semantic type of M is the image of some simple type of PTT, and that any section of M, of a display map of M, is the image of some term of PTT. We would like M to have this property. Now I tell you why. Assume that we have such a model. So a model with this surjectivity property. Now we can, if we have such a model, we can actually deduce conservativity in this way. Assume that you have a simple type judgment, capital T, okay? And this in PTT, right? Now interpret it in ETT and assume that there is some proof of the interpretation in ETT, which here I call small a. So since M is a model of ETT, it needs to believe this judgment, okay? Which means that there is some section, right, of the corresponding display map associated to the interpretation of T. right? But M has the property that the interpretation of PTT is surjective, right? So this section will also need to be the image, okay, of a judgment, of a term judgment in PTT, right? Because M has this property of a surjectivity of the interpretation of PTT. So there is some simple term judgment, B, in PTT, which is sent in that precise section, okay? And then some initiality argument, delta needs to be exactly gamma, and S needs to be exactly T. So PTT finds a term B, which lives in T. With the hypothesis, I tell you again that the same happens for the extensional type theory. Okay, so this is how you prove the conservativity result. Right. Well, I guess there's no time to go through the construction of M, but let me just say that, of course, the idea is that you wanted to build a quotient, to perform some quotient of the syntax of PTT, right? In such a way that any path is identified with the reflexivity loop. But you cannot just do that, otherwise you lose all of the dependent type theoretic structure, right? So basically the rules of the strict substitution. So it would not be a model anymore. If you want to think a category theoretically, you will not get a category with attributes with the Cartesian natural transformation. With maybe the natural transformation is still natural, the family of display maps, but for sure it will not be Cartesian. You would have several possibilities to define the substitution, and this we do not want. So the idea is that you have to identify paths with reflexivities, but at the same time maintaining the structure of the category with attributes. So you need to define a thing that is called canonical homotopy equivalencies between contexts in such a way that these two properties, once you quotient, are satisfied. I will stop here. Thank you so much.
Is there any question?
Thanks for the talk. So I was wondering about this initiality that you use in the proof,
right?
That you mentioned before. Do you mean like that? So is that the initiality of the model M?
No, initiality of the syntax of ETT. Because the syntax of ETT can be made into a category with attributes, right, which is the initial among.
Okay, so you use that initiality.
Yes.
Okay. All right, thanks. And then maybe a clarification with the basic type judgment. You mean one in the empty context? Or
no.
What do you mean by basic?
Usually, yeah. Usually they are given in empty context, right? I mean, in general, I mean types that are given that are not the result of the application of a sigma pi.
So like the atomic predicates.
Yeah, basically the axioms of the rules without a premise, let's say.
And you have not considered what happened with the universe?
No, that's right. I didn't consider with the universe, which in fact, that is also needed to provide a. That is why before I said that what I was saying was not formal when I talked about foundations, right. Because of course to give a foundation, you also need a tower of universes, right? So, yeah. Right, it should be done with a tower of universes as well, but I didn't consider it still.
Okay, thanks.
Thanks.
I have more questions, but
Third question. Can I ask just about this last construction? So it is syntactical, but you have to. So do you have to use some choice principle in the meta theory to?
Yes, yes. Up to now, yes, but from a discussion with Milli Maietti, it seems that one should be able to. I mean, I still have to see whether it works in this framework, but Mili Maietti and Michele Contente in a simple, in a similar framework, have a way to avoid the use of some sort of choice in the meta theory, which I was suggested to see if it is applicable even in this framework.
Okay,
Thanks for the question.
So let's thank the speaker again. And we go on with the last speaker, which is Andrea D'Aretto. And the title of the talk is Categorical Semantics for Counterpart-Based in Agda.
Dov'è il puntatore?
Puntatore.
Okay, thank you everyone for being here. Today I'll present some work I did during my master's thesis, which lies at, let's say, the intersection of temporal logics, proof assistance, and category theory. So to summarize essentially what I'll be talking about right now, I'll essentially present the categorical semantics of temporal logic, which is based on the counterpart paradigm, which I'll explain shortly. And I'll present some insights, let's say some brief summary of what we've learned and done by formalizing these categorical structures using a proof assistant AGDA based on dependent types, and a library for formalizing categorical constructions, which is called AGDA libraries, AGDA categories. So first, I'll start by presenting a brief introduction to temporal logics and counterpart semantics. And then I'll move on to the categorical perspective on the semantics of these logics and their models, and then give some insights on the formalization in AGDA, and then conclude with some future work. So temporal logics in a single slide, more or less. Temporal logics are essentially a formalism for specifying and verifying the properties of complex software systems. And the idea is the following. You represent your system of interest as a transition system, which we call the model. And this is an example of a transition system for a simple vending machine. So you start from the base state, and the only transition available is to go into the select state, where you can select the beverage that you want to buy. And for example, you might either want to get tea, or you might want to get coffee as possible evolutions of our system. And the idea is to express the properties that you want your system to satisfy as formulas in the temporal logics. So for example, you might have the following formula, which says that always you eventually end up in the state where you pay, right? But you do not have, for example, that you eventually end up in a state where you have the tea, that the machine gives you tea, because you might want, for example, to always get only coffee, right? So you go from pay to coffee select, pay coffee select forever. And then the idea is to use a program which automatically checks that these properties that we specified in this formal language are satisfied by the model or not. So what we've seen so far is that states are essentially atomic points, right? They are not decomposable in any sense. But in practice, often the states of a software system have more structure that can change over time, right? When you do a transition, for example. And so, for example, we might want to model the time evolution of graph topologies, where the states themselves are graphs. And you want to model the merging of nodes in a graph, the deletion of edges, for example. Or you might want to model processes in memory, right? So a state is a collection of processes which can be forked, deallocated, and allocated. Or you might want to model for example, election algorithms, right? So you have parties which can evolve, split, unionize, and other things in time. So the objective of the counterpart semantic I'll present shortly is how do we enrich these models, such as the transition system we've seen the first slide, to express this kind of multi-component behavior, and how do we define some logics which can express the properties and reason on the fate of individual elements inside of the states? Well, the answer is yes, using counterpart models and quantified temporal logics. So in standard linear temporal logics, which are essentially the elementary starting point for temporal logics, you have that you consider sequences of states, right? So these are called traces, and by the color here, for example, red and blue, we indicate some kind of property that we want to identify over some states, right? So we want to say the state I'm currently in is red, and the next one is going to be blue. The idea of the counterpart paradigm is to associate to each state a set of individuals, which we call worlds. So our traces are essentially sequences of worlds, and the properties are not on the states themselves atomically, let's say, but they're on the individuals inside of the world. So, which we denote here by the different colors. Now the question becomes, how do we represent transitions between worlds? The idea is to use counterpart relations, right? So counterpart relations are relations in the usual mathematical sense of subset of the Cartesian product of the two worlds. And the intuition for these counterpart relations is that the two elements in a world, from a world to the next one, are connected when intuitively they are the same individual after one temporal evolution, after one step. And we call these sequences of worlds and relations connecting them counterpart traces. Now, having defined these models, we can define a temporal logic on these kind of models, on counterpart traces. And the presentation of a temporal logic is essentially the standard one. So you have the usual propositional fragment, and then you have two temporal operators, which I'll explain shortly. And then we actually have this temporal logic is a quantified one, right? Because we want to reason on individual elements of the state. So we have three different kinds of formulas, for example, identifying the two individuals as being the same, expressing the existence of an individual in the current world, and a generic unary predicate for individuals. The semantics for formulas is that you essentially give for each world in your trace, you define the tuples of individuals which satisfy a given formula phi. So let's see an example. So we take the model we saw before, and I'll use this notation of validity to indicate essentially that this individual in this world satisfies the given formula, where x is essentially a variable which, for simplicity, will just refer to the individual we'll be talking about. So in this case, we have the A0 in the first world satisfies the formula next red of x, because there exists a counterpart for A0, namely A1, in the next world, such that the formula red of x is satisfied for A1, right? And for example, we have in omega 1, C1 does not satisfy next red of x, because there is no counterpart at the next step which satisfies red. And C0, so I'm giving you the intuition for the next operator right now. And the intuition for the until operator is essentially the following one. So you start with C0 in the first world, and you have the blue until red, right? And the intuition is essentially that you start by seeing the first world that you're in, and see whether the first formula is satisfied or not. And you want to say there exists a world after some steps where the second formula is satisfied. And the first formula is satisfied for all steps leading to it. So you have C0 is blue. There exists a counterpart B1 for C0, which also satisfies blue, a counterpart B2, which also satisfies blue. And finally, there exists a step after some temporal evolutions where the second formula is satisfied. Why did I say tuples? Because actually you can have not just one individual satisfiability for formulas, and that obviously corresponds with the notion of free variables of your formula. So you have, for example, that together A0 and B0 in the first world satisfy next x equals y, right? Because you have a counterpart for both elements in the next world such that x is identified with y. And this actually, you can see, allows us to model the merging of two elements. You can also have the empty tuple, and this essentially expresses the fact that the formula is closed, right? It has no free variables. And you can say, for example, in the third world, omega 2, that there exists an x such that next blue of x. And in this case, it would be C2, right? Because in the next world, there exists a counterpart which is blue. Another a bit more contrived example is that you can take A0 and C0, and you have that these two elements are different until there is a point in time after some temporal evolutions where they become identified with the same element, namely A3, right? Now, so far, we have only seen traces, but this can easily be generalized to counterpart models, which are generic transition systems, so not just linear sequences of worlds. So a transition system enriched with worlds and counterpart relations between them. And the main claim and the main idea of this talk is that these counterpart models can be understood within the perspective of category theory. So a counterpart model is essentially identified with these data. So you take a category W, a class T of selected morphisms of W, which you call temporal structure, and a presheaf D from W up to rel, where rel is the category of sets and relations, which you call relational presheaf. What's the intuition behind this? Well, as you might imagine, the objects of the category are identified with the states of the underlying transition system. And so the objects of W are essentially points in time, right? And the morphisms of W represent the transitions between states, right? So it's like a temporal evolution for a given world. So you go from one instant of time to the other, even by possibly other different morphisms, because the state might evolve in different ways. And the temporal structure is used to identify the one-step transitions of the model. And the relational presheaf in the counterpart setting assigns worlds and counterpart relations to states, right, in the intuitive way. So let's see a very simple example. So what's the usefulness of the temporal structure here, which I highlight in red? Well, in a category, you have identities and compositions, but you don't really have a notion of what it means to evolve in one step, right? And we actually don't have any constraint on this temporal structure. You don't need to have any kind of connectedness or having all objects that they have some sort of evolution with the temporal structure. And so you take a category and you essentially embed it into the category of sets and relations, and you obtain the counterpart model, right? Now, how is the semantics of the logic defined? Well, usually in temporal logics, you define relation inductively between formulas and tuples of individuals for each world. And the categorical way of doing this is essentially via a tool called classical attributes, which is essentially, let's say, first order notion of satisfiability. And the idea is that for each world, you define the sets of individuals in each world which satisfy the formula phi. So you identify not all the individuals, but just a subset of them, which actually do satisfy the formula, right? This is the perspective of categorical logic. And so here's just to give a bit of a formal definition, right? So a classical attribute A on a given relational presheaf D is a family of set for each world omega in W, such that A of omega is a subset of what the presheaf assigns to the world. So a relational presheaf gives us a common universe of elements, and a classical attribute is a given property A. So you say that an individual in a given world is part of the classical attribute A when it satisfies this property A. So let's assume to have a counterpart model, right? And to give these semantics for formulas essentially amounts to giving, first of all, assigning a relational presheaf to context, which is essentially done by iterating the product of a presheaf in the usual pointwise sense, right? N times, right? And this essentially gives us a tuple of individuals for each world of the category. And so the semantics for formulas are given by a classical attribute on this the relational presheaf we just defined, which is the context of the formula. So for example, you have the false is identified with no elements, right, for each world. And the true formula is identified with the entire presheaf and all the individuals in the presheaf. So you have the usual definition that you can imagine. So disjunction is just union. Negation amounts to set complementation. So, equality is essentially defined by taking the appropriate projections from the Cartesian product. And existence then is defined by saying that there exists a B given by the presheaf such that AB satisfies the formula, right? And how is the semantics of temporal operators given? Well, it's actually a bit contrived, but the idea is to take a presheaf X, which is essentially the context that we're working in, and two classical attributes, A, B, which are essentially the semantics of the subformulas of the temporal operators. And so we define new classical attributes, which combine these classical attributes A and B. So we define a next, we're not going to go too much into the details of this. We can define a new classical attribute next of A, right? If for every temporal development in the category, there exists an element, right? An individual Z, which is a counterpart of S, right? And this is given by this, right? So when you take the pre-sheaf and take the temporal, where this is in the relation, and you want Z to satisfy the formula A. And for until, you have more or less the same idea. But you need to be careful because you are talking about paths, right? Paths from a given world omega as given by the temporal structure, right? And you want to, for example, universally quantify over them. So over all possible temporal evolutions from a given starting point, you want this to be satisfied, right? And now, yeah, but the important thing is not too much in the detail because it's just the intuition I was telling you before. But the important thing is that you have A and B as the classical attributes for the subformulas of A until B. And this is just you have a neat definition of the semantics of temporal operators because you just use these classical attributes here compositionally. Now, how are the classical semantics, the classical inductive semantics and the categorical one related and their models? Well, they actually have a good result. So the classical models and categorical models are in some sense equivalent because for any classical counterpart model, which is just a transition system, right, for sort of that one, there exists a categorical counterpart which satisfies exactly the same formulas, right? And the idea is actually the one you might be thinking of, where you construct a freely generated category W from the transition system. So you take as objects of the states of the transition system as objects, and then transition as morphisms, and then define a relational pre-sheaf assigning worlds and relations. And then you restrict the morphisms which are generated by the category with the temporal structure T. And the interesting thing, which since we're going to be talking about the formalization later, is that this theorem here has not been formalized, but the construction that gives rise to it has. So this is going to turn out to be useful later when we'll talk about the relationship between classical and categorical semantics. And a very interesting extension of this setting is that we actually want to, in practical settings, to not talk about just sets of individuals, but we actually want to have more structure on them. So we want to talk, instead of sets, we want to talk about many sorted algebras over some signature. So we're going to need a bit of a tech for this. The first one is the notion of relational morphism between two relational pre-sheaves. And this is essentially the notion that we'll to express the fact that algebras and transformations relations between them have to to preserve the structure of the algebras. So you have two relational pre-sheaves X and Y, and you define not a natural transformation between them, but a family of set functions between them. And this you will see corresponds with the intuition that in algebras you talk about functions and not relations. And so you define a family of set functions for each world, such that for every error in the category, the two elements are related by X, if and only if they, and they're not if and only if, it's just an implication, right? So if they're related before, they're also related after the transformation. This is intuition. And how do we extend the models? We essentially take, let's say, sigma, many sorted signature. An algebraic counterpart model is just a tuple where we have omega and T, which are in category and the temporal structure the same as counterpart models. And S is going to be a family of relational pre-sheaves, which assign a relational pre-sheaf to each sort of the signature, of the signature, yes, and which we indicate with these semantic brackets. And then we're going to be having a family of relational morphisms, F, which gives an interpretation for each function symbol in the signature, right? And where the function symbol is assumed to have this signature, then this is the type, right, of the relational morphism of the given by the family. And as I was saying, this the fact that these are set functions is essentially, and that this condition is satisfied means that these morphism preserves the structure given by the algebra. So let's give a very simple example. Let's take the signature of directed graphs. So we have two source, node, and edge, and two function source and target with these signatures here from edges to node, which represent the source and target. And we have, for example, this counterpart model on the signature of graphs, of directed graphs, actually. And we have this graph in the first world, which gradually gets shrunken down to a smaller graph. And so the data that we need to provide is a relation between nodes, first of all, and then a relation between edges. Right? And actually, these essentially correspond to homomorphism of graphs where the relation between them is a relation, not necessarily a function, right? And then we can talk about, we can extend the logic that we introduced before, and we don't just have equality of terms of the logic, but we can talk about the equality of terms of the algebra. Sorry, not individuals, but terms. So for example, we can have a macro which says that a given element E, an edge, is a loop, right? And we can say that E5, for example, in the last world is a loop. But we can also use the temporal operators, obviously, to express, for example, that E4 at the next step will become a loop, because obviously there's a counterpart relation that evolves to E5. And this is just to give a graphical intuition for what's going on in the categorical setting. And so you have two presheaves, which for each sort of the algebra, right, which identify both the evolution of the nodes and the evolution of the edges. And then you have these kind of not really natural transformation, but set functions for both the source and target, right? Right. Now we're going to be talking about a bit about the formalization. So AGDA is a proof assistant, essentially, which is based on the dependent types and also doubles down, obviously, as a programming language. And it can be used in practice to formalize these kind of mathematical constructions. And our work essentially consisted of formalizing this categorical semantics of QLTL in AGDA, and using the AGDA categories library, which I'll be talking about shortly. And with this kind of extension of algebraic QLTL, which also required a bit of work in trying to formalize multi-sorted signatures in AGDA. And we've also formalized classical set-based semantics to, let's say, popularize a bit this kind of counterpart paradigm without the use of categorical logic. And also a brief presentation of the positive normal forms of QLTL, also in AGDA, which is related to an interesting problem due to the intuitionistic, right, nature of dependently typed proof assistant. So just to give you a bit of numbers, which is more or less 1,300 lines of code for the categorical semantics, and the positive normal form includes also the classical semantics. And why is giving a formal presentation of the logic a useful endeavor? Well, first of all, because it formalizes the correctness, more or less, of the construction we present. And we actually, by formalizing in a constructive proof assistant, you have a playground, right? A formal setting where you can experiment and test your logic. And actually, giving this semantics with a verified tool also establishes like a foundation for verified model checkers. So you not only have your model checker, which verifies your program, but the model checker itself is verified in some sense because you formalize the semantics that it's trying to capture. And given the constructive interpretation, again, you also practically have a program which can convert standard models given by transition systems into the categorical ones. Because as I mentioned before with the theorem, we actually have a procedure which converts the standard models into categorical ones. And the workflow is more or less this one. So you can define the semantics of your logic using categorical notions in some sense. And then the user, for example, might want to provide a standard non-categorical transition system as the model of interest. And then you use the procedure that we have defined, which constructs the categorical model from the classical one, so that you can apply the semantics that you've defined using categorical tools. So how did we formalize category theory things in a proof assistant? Essentially, we used this library called AGDA categories, And it's quite interesting to talk about some of the design choices of the library in the setting of proof assistance, especially, and some useful remarks and interesting ones that essentially characterize this kind of formalism in proof assistant is that, for example, they choose to give an internalized notion of equality between morphisms in categories. Right? So you have a sort of this kind of opaque equality for morphisms between the categories, between morphisms between two objects. And this is essentially done to avoid having to postulate extensionality principles, which are something you need to postulate in AGDA, for example. And this, as an implication, also means that you need to do this kind of setoid equational reasoning in proofs, which can turn out to be quite annoying because you need to always reason up to setoid. And you also need to have additional coherences, which are needed when you work with these setoids. And for example, when you define a category, you also need another piece of data, which says if that composition behaves well with setoid equality, for example. And in functors, you have a similar thing, where you have that in category C, if F is equal to G in the setoid, then they're also equal with the action of the functor on morphisms. Another interesting design choice of the library is that they essentially define two associativity fields, one of which is actually redundant because you can define associativity, but they also provide sim associativity. So it's just swapping, right? The two sides, the left-hand side and the right-hand side of the data, and this is done so that taking the op of a category twice becomes definitionally equal to C. This is an interesting thing that was also documented in an article by in 2014. So how was our experience with AGDA categories? Well, essentially, we are quite pleased to work with it because we were quite pleased to work with it because it's really practical and flexible, because there is no magic there in some sense involved in the library. It's all defined in AGDA itself, right? And these design choices that I've shown you so far do not necessarily always get in the way of practical applications. Maybe when not using categories as data, more or less, but trying to formalize theorems, these design choices do get in the way. And the main definitions used are actually not too complicated, because we just use categories and functors as data for our models. So categories, functors, the category of sets and relations, free categories generated for a quiver, which is called path category in AGDA categories, presheaves, and an interesting fact that category presheaves is complete, relational presheaves and morphism between them, which wasn't actually too difficult to formalize. And so, as I mentioned, the functoriality and setoid equality preservation can be a bit of annoying to prove, but not necessarily too hard. They're just, let's say, a bit of a bookkeeping that you need to do in order to work with the library. But again, these definitions and notions are not too theoretical. They're not too in-depth into the categorical perspective to, let's say, stress test the library in our setting, right? And I think I'm going to be skipping this part, as interesting as it is, because there's not too much time. And so just to conclude, and as we've seen, I presented a sketch of the categorical semantics of counterpart-based temporal logics, and told you a bit about the formalization in AGDA. So there are many possible extensions of this work in many different directions. For example, on the temporal logic side, we could expand and extend QLTL to express set quantification with the second order QLTL, or also consider different kinds of temporal logics, such as CTL and CTL star, which actually have, let's say, more expressive, more complex models. And another interesting thing would be to see whether a proof assistant can be easily interfaced in the context of model checking to use external solvers and be more efficient when, for example, providing counterexamples or proof searching for temporal logic formulas. And another interesting thing on the categorical side is that we could formalize the syntax and the model of our logics using the tools of categorical logic. So using index categories and morphism between them to also provide the syntax of the logic itself. And as of now, a study of temporal logics presented with a proof assistant is still absent in the literature. So there's not too much about it. There's some work by Nipkov. And another interesting aspect that is starting to rise up is that these kind of decisions that need to be taken when designing a library for reasoning with category theory, and categories. And there's not too much work about it, but this first article here is the documentation, let's say, the rationale for some of the design choices of AGDA categories, and another work in Koch in 2014, which talks about other interesting aspects of formalizing category theory in Koch and proof assistance. Thank you.
Okay. Any question? Okay. So if there are no questions, I think we can conclude the session here, and we thank the speaker again.